Okay. Oh. All right. You guys are going to see how the sausage is made. We're going to change this quick to Osteogenesis at the top here. Oh, no. No, move that around. All right, good. Good enough. All right, osteogenesis. Let's talk a little bit about bones, how bones are made. This is a... I'm running out of ideas for the ChatGPT images. This is a tattoo of osteogenesis. I kind of want to get this tattoo. I don't have any tattoos, but I'd like to get a tattoo. I don't know if I'd go full sleeve right when I got my first tattoo. All right. I gotta get one before my skin gets all wrinkly because I'm old. All right, here we go. Schematic diagram of endocardial ossification. Ossification meaning the formation of bone tissue. Focus, camera. Focus, thank you. All right. Part A. Let me get my pointer, laser pointer. All right, part A over here. So we have the mesenchymal cells that commit to becoming cartilage cells, chondrocytes. So we kind of talked about this in the previous lecture, that the sclerotome and some of these different tissues have kind of predetermined roles and what they're going to be. So these are the mesenchymal cells that are going to be cartilage. The committed mesenchyme cells condense into these compact nodules. Then the nodules differentiate into chondrocytes and proliferate to form the cartilage model of bone. So we start with cartilage as like the form, and we cast upon it, like using art terms, I guess. I don't know if those are the correct art terms, but we have the cartilage that forms kind of the model, and then it'll be ossified. So part D here, we have the chondrocytes undergo hypertrophy and apoptosis, so they die, while they change and mineralize their extracellular matrix. So they kind of die off and they start to ossify or add calcium and what is needed to make bone. Then we have, once the apoptosis of those chondrocytes happens, this allows blood vessels to penetrate and grow within the developing bone tissue. We have blood vessels then bring in osteoblasts, which are bone creating cells, and this binds to the formerly cartilaginous matrix, so the cartilage that's breaking down, and it starts to deposit bone matrix in its place. So it comes in and replaces all that cartilage with what's going to be the bone ECM, or extracellular matrix, and then the bone formation and growth. This consists of ordered ways of proliferating, hypertrophic, and mineralizing these chondrocytes. So like making chondrocytes as a mold, breaking them down, replacing the cartilage with bone over and over and over again. And then the secondary ossification is when these blood vessels enter and they bring those osteocytes to aid in the ossification process. The secondary ossification, this centers around this process at the tip of the bone here, right? So there's kind of like a secondary process of the osteocytes coming in and forming its own breakdown and restructuring at the tip of the bone. All right, so let's look at this this endochondrial or endochondral ossification. So long bone, so like your femur or whatever, which is undergoing this endochondral ossification. So the cartilage in this case is stained, is labeled, I wouldn't say stained, blue. So the cartilage is stained with Alcian blue, and the bone is stained with alizarin red. And so then they also tried to kind of mirror it in this diagram here with blue and peach. I don't know why they did that. Anyways, so the cartilage is stained blue and the bone is stained red or peach. And this is kind of shows the transition zone where the chondrocytes, or those cartilage cells, start to divide, enlarge. So they start here, the reserve chondrocytes, they start to proliferate, they enlarge, and then they die, and then are replaced by osteocytes, or these mature endochondrial bone cells over here. So they kind of grow up, and then they end up die. So they're still there, but they're not actively proliferating, and instead are becoming ossified in bone cells. Okay, so during this process of endochondral ossification, we have these paracrine and transcription factors that are active in the transition from cartilage to bone. The mesenchymal sclerotomes, we talked about the sclerotome previously, those cells can become either chondrocytes by exposure or activation via SOX9, so we've talked about SOX9 a few times now, or they can become osteocytes, so chondrocytes or osteocytes, and this osteocyte, this Asterix transcription factor, is what causes them to become osteoblasts/osteocytes. And this depends on the paracrine factors it experiences. So remember, juxtacrine or paracrine, so depending on gradients, we're always talking about gradients, the gradient of the paracrine factor, if there's a lot of SOX9 around, they become a chondrocyte. There's other actors along the way, WNT, BMP, the things that we talk about a lot. And then this parathyroid hormone-related hormone that can acts as a repressor at some points of some things too. Anyways, more important, SOX9, WT, BNT, or BMP, those lead to chondrocyte, cartilage cells. Asterix forms osteoblast. You can transition from a chondrocyte to an osteoblast through this specific pathway. Don't worry so much about that. So let's see. Funny enough, so what's funny here is that IHH is, for some reason, another. So there's Sonic Hedgehog. This is Indian Hedgehog. Don't know the story behind that name. But Indian Hedgehog can be expressed by chondrocytes, which represses twist. And so then it can turn on bone-specific proteins. Anyways, I just think it's funny that another kind of jokey name of a gene, Indian Hedgehog. All right. So this is phenotypes. Phenotypes, traits, right, can be produced by stress force on muscular and skeletal tissue. So in these images here, the fibular crest, which is right here between tib-fib, right? So in between your tibia and your fibula, which connects the tibia to the fibula, is formed when the movement of the active embryo inside the egg puts physical stress on the tibia. So some of this development, when we talked a little bit about this with the notochord, that we talk a lot about gradients, gene expression, who your neighbors are, paracrine factors, juxtacrine factors, etc. There's some aspects, and like I said, we talked a little bit with the notochord, that mechanical force or stress can also aid in development. It's a kind of a minor player in the overall pantheon of development. But in this case, this movement of the chick embryo, it's getting to that age where it's able to move. That is what leads to development of some connective tissue. In this case, the fibular crest. So this is day 13 of a chicken embryo in part A here, and then you can see it's stained here blue, where we have this connective tissue between the tibia and the fibia. In part B, I don't know how, but experimentally, they prevented movement of the embryo, of at least the eggs of the chick embryo. And as you can see, that prevented the development of this fibular crest. So, because there's no mechanical force, it's just sitting there, right? And so just like the notochord, and we don't really, I can't remember if we talked about, I think I cut that lecture. Anyways, there's a couple small aspects of where like physical force causes, impacts development, and this is one of the cases here too. And then lastly, this is kind of like a later development thing. So it's past, we would put this, if we looked at our life cycle of development, where you have fertilization and cleavage and, gastrulation and organogenesis, blah, 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 blah. Metamorphosis. So this is a later development aspect where this is a cichlid fish, and the growth of its jaw is dependent or impacted by the hardness of its food. So even after birth, so we still have development. We talked about with like brain development with humans, like, or with, especially people your age for the most part, most of your age, like your brain's still just finalizing development. So it occurs well after birth. In these fish, even anatomical things like your jawbone is still developing. And so the size and aspect or anatomy of your jaw is dependent on the hardness of the food that they eat. So if you give them very hard food, they will develop a different jaw structure where they need a bigger, more forceful jaw to eat, say snails, or I don't know exactly what they eat, but say snails or something that you would imagine would be difficult and crunchy. But if you give them like fish flakes or something very easy that they don't really exert that mechanical force, then they don't develop that way. And it's one thing where it's like, okay, I can understand, if you have hard food, your jaw muscles are going to be exercised more, so they're going to be bigger. But this is an x-ray, right? So you're seeing differences in bone structure. So you can see that this giant long jawbone here compared to this itty bitty jawbone here, that is implicated by this mechanical force. So while it's not terribly, it's not a huge aspect of development. It is kind of a niche aspect where the mechanical force or stresses. There is theories that twinning, so becoming a twin, could be impacted by mechanical force as well. That'd be early on in like cleavage stage, etc. But anyways, yes, mechanical force does play a role in development in some cases. All right, and I'm gonna stop there. 15 minutes, boom, just under 15 minutes. Thank you for watching. I appreciate it. I hope you enjoyed the lecture, and I'll catch you in the next video.